Yes, so I would like to thank the organizers for allowing me to share some of our recent work with you. I will talk about non-reciprocal binary fluid turbulence. So this work has been done with Biswajit Maji mainly, who's sitting there, so he'll answer all the questions. Nadia, who is in Dresden, and Axel Voigt, who's also there. And I'd like to acknowledge support from all these agencies. All right, so here's an outline of my talk. Non-reciprocal, henceforth NR systems. Then first the non-reciprocal Kahn-Hilliard system and the non-reciprocal Kahn-Hilliard-Navier-Stokes system. And we will show that this non-reciprocity will lead to a new form of turbulence, which we will call NRCH-NS turbulence, and we will characterize it by the means that we use to characterize different forms of turbulence. There's a preprint out on the archive, which you can look at for details. So non-reciprocity is quite old, but it seems to be enjoying a renaissance. I show you some examples here in Nature, PRX, PNAS, and Nature Communications. And well, I mean, people like interesting titles in this field. So they say when Newton's third law is broken, but of course, when they are careful, they say that generally the action-reaction symmetry can be broken for mesoscopic particles when their effective interactions are mediated by a non-equilibrium environment. So please don't think that Newton's third law is being violated. So let me give you a simple example of such non-reciprocity. If we have two scalar order parameters, phi and psi, all right? And we just ask, and they're both conserved, then we know that they follow the Kahn-Hilliard system. They phase separate, and the equations that govern their phase separation are given there, except that now, instead of having something which is derivable from a Landau-Ginzburg type free energy, I put in some terms here, d1 2 psi and d2 1 psi. If they were derivable from a Landau-Ginzburg free energy, these two coefficients would be the same. But if you allow them to be different, that is the source of non-reciprocity in these systems. And they've been studied in a fair number of recent papers, and this non-reciprocity leads to some very interesting effects, including waves traveling through the system and so on. But in spite of so much interest in non-reciprocity, somehow there has been no investigation of non-reciprocal turbulence, and then we have written down this set of equations, which, as far as I know, is the first examination of non-reciprocal turbulence. So it's really straightforward in the sense that I take these non-reciprocal Kahn-Hilliard two scalar field phi and psi models, and then I add them to a fluid, so there's an advection of both the scalars by the fluid. And then if you go back and look and keep track of all the terms, this is how the scalars act back on the fluid. That's some friction. The fluid is incompressible. And similar models have been written down for very low Reynolds number studies of such turbulence, okay? Not turbulence, nothing, only flows, okay? So we will now examine this by using simulations, which I will not describe in detail, but the important parameter will be the ratio of the off-diagonal terms in the diffusion matrix to the diagonal terms, all right? And we will see that as you change viscosity, so you're already seeing one simulation at low viscosity, you get turbulence. At high viscosity, you get these bands, these waves. Basically, the high viscosity limit, oops, it went away. All right. high viscosity limit was what was studied for the non-reciprocal Cahn-Hilliard system. You can also drive this turbulence, oh God, it takes a little while to recover, by changing this non-reciprocity parameter, okay? And as the non-reciprocity parameter increases, you get flows which are obviously turbulent, and at least at the qualitative level, I hope I have convinced you that we have a new form of turbulence. Now, of course, if you're a hard person, you'll say, I don't trust all these pictures and movies. Give me some spectra so we can define suitable spectra and so on, which I will show you. But the most important term here is something called a non-reciprocal flux, which has been used by the people who have studied these systems at low Reynolds or in the no coupling to fluid limit. It is phi grad psi grad phi minus that averaged over all of space. And we will see that this object is important in these systems. So let me just show you a few plots. So this is the energy of the system versus time, and the oscillations have to do with the turbulence that has been formed. These are other lengths which I can define, but probably I don't have time. Now let's look at this parameter, this flux, the non-reciprocal flux. In the high viscosity or low Reynolds regime, it goes to a fine value. But as the turbulence increases, it decreases and fluctuates. It doesn't go all the way to zero, so it is still non-reciprocal, but it is fluctuating. And the very turbulence which is generating it is also reducing it. You will also perhaps know that if you have this phase separation of two scalars, if there is turbulence, that tends to mix them up. And here too, this non-reciprocal turbulence does mix up the scalars, right? You can study various spectra and so on. You saw in the previous talk examples of compensated spectra. So here also you get compensated spectra. The scaling range isn't huge given our numerical resolution, but there seems to be a minus 5/3 regime, which, if analyzed by the methods of turbulence, seems to be an inverse cascade. But it's not trivial 2D fluid turbulence insofar as it is non-reciprocal. I have shown you that by plotting this J of t. You can do intermittency, flow topology. Let me not go through that because this monitor is telling me to conclude. So here are the conclusions. We have developed a model and uncovered this new type of turbulence, which is non-reciprocal. The non-reciprocity comes from the scalars. It is not there explicitly in Navier-Stokes, but only there implicitly. So I thank you for your attention, and I'll be happy to answer any questions if you have any.
It's time. Questions?
Yes.
In Kuramoto and all, non-reciprocal just means that Kij is not equal to Kji.
Yes.
In that case, you get periodic order parameter or chaotic order parameter.
Sure, I'm sure.
So you get something like this here?
Okay, I guess I'm old-fashioned. I use the word turbulence for hydrodynamic turbulence. You can have, of course, in other dynamical systems, spatiotemporal chaos and so on. Yeah, of course, absolutely.
More?
Experimentally, is it like, how do you introduce such non-reciprocal? Is there some simple way?
Okay, good, tough question. There are examples, Bishwadit and I will show you afterwards, where people look at crowds, not clouds, excuse me, and they claim there are some examples, but there is no bona fide non-reciprocal binary fluid system. But we are looking, and with enough looking, I hope to be able to find some.